Why does classification matter in machine learning, you might wonder? Well, let's dive into this. In the vast ocean of data, classification serves as a compass, helping us predict the category or class of data points. It's like sorting apples from oranges in a mixed basket, but of course, in a much more complex manner. Here's how it works. It's a two-step process, much like learning to ride a bicycle. First, you learn how to balance and pedal. That's your training phase. In machine learning, we feed our system with training data, teaching it to recognize patterns and correlations. Then comes the second step, the actual ride, where you put your learning to test. Similarly, the model we've trained now uses its learning to predict the class for new, unseen data. So it's clear that classification is a pivotal part of machine learning. But how do we go about it? One popular method is linear SVM classification. Linear SVM classification sounds complex, doesn't it? But fear not, it's simpler than it sounds. Let's break it down together. First off, SVM stands for support vector machine. It's a method used in machine learning and statistics. But what's it for, you ask? Well, its primary purpose is to find the best hyperplane that separates two classes of data. Now, don't get intimidated by the term hyperplane. It's essentially a subspace whose dimension is one less than that of its ambient space. If you're thinking of a two-dimensional space, a hyperplane would be a line. In a three-dimensional space, it would be a flat plane, and so on. But how does SVM do this? Picture two groups of data points on a graph, each belonging to a different class. The goal of SVM is to find a line or a plane or a hyperplane that not only separates these two groups but also stays as far away from the closest points in each group as possible. These closest points are known as the support vectors. Why does it matter to maximize this distance or margin? Well, the larger the margin, the lower the generalization error of the classifier. In other words, a larger margin makes our model less prone to overfitting. It also increases the model's ability to accurately classify new or unseen data. Here's an interesting fact. Only the position of the support vectors matter in defining the hyperplane and margin, not the other data points. This makes SVM less sensitive to outliers and allows it to handle large datasets efficiently. So, to sum it up, linear SVM classification is a method that finds the best hyperplane to separate two classes of data. It does this by trying to maximize the distance between the hyperplane and the closest points from both classes, known as the support vectors. This method is particularly useful because it helps reduce overfitting and increases model accuracy. And just like that, the seemingly complex concept of linear SVM classification is broken down into simple, understandable steps. Now that we've simplified linear SVM classification, let's consolidate our understanding with some key points. Firstly, let's remember that at its core, linear SVM is a supervised learning model used for classification and regression analysis. It's all about finding the best hyperplane that distinctly classifies the data points in an n-dimensional space. This hyperplane is our decision boundary, the line that optimally separates our classes. One of the most significant aspects of linear SVM is the maximization of the margin. The margin in this context is the distance between the nearest data point from the classes and the hyperplane. The SVM algorithm is designed to find the hyperplane with the maximum margin, which is why it is often referred to as a maximum margin classifier. This feature makes SVMs incredibly robust and enhances their ability to generalize well to unseen data. Now let's talk about the versatility of linear SVM. It shines when dealing with both linearly separable and non-linearly separable data. With linearly separable data, the algorithm creates a straight line or plane to separate the classes. But what about when the data isn't linearly separable? Well, that's when the SVM uses something called the kernel trick. By mapping the data to a higher dimension, it can find a hyperplane that separates the data even when it initially seemed impossible. Another point to note is the efficiency of linear SVM. It's a powerful tool that can handle high-dimensional data, making it an excellent choice for tasks like text classification, where the dimensionality can be extremely high. In conclusion, linear SVM classification is an essential tool in the machine learning toolkit. It's versatile, robust, and efficient, capable of handling complex high-dimensional data and finding the optimal decision boundary. So there you have it, the key points about linear SVM classification, a powerful tool in machine learning made simple.